All right, let's take a look at this model of an atom at the top. And let's start listing off by listing its physical properties. What are things that we can see, things that we note. So just by looking at the model, I can see that there is some big circles in the middle. Some are shaded, some are not. And then there's these sort of like ring-like structures that are kind of look like walls around the center with these smaller black dots around it. So actually, this model shows how subatomic particles look inside of an atom. If you don't recall what subatomic particles are, they are the protons, the neutrons, the electrons. This is how they are inside of an atom. So in this case, we're going to say that these shaded circles are the protons. The not shaded regions that are next to the protons are going to be the neutrons. And these smaller shaded circles towards the edges that are around the circle are the electrons. And this is how they look like inside of an atom. And now that we have these subatomic particles labeled, let's add them onto our graph. So we have the protons, we have the neutrons, and we have the electrons. And so each subatomic particle in an atom actually has a different charge that helps stabilize the atom. So a proton has a charge of +1. A neutron has a charge of 0, and an electron has a charge of -1. All right, and now we're going to move on to the mass. So although we do have a model of the protons, neutrons, and electrons here, the actual drawing of them would be way smaller than this. And because of their small size, scientists decided to create a new form of measurement specifically for these subatomic particles called AMUs, which stands for atomic mass unit. Atomic mass unit is based off of the weight of a proton. So in AMUs, 1 proton is equal to 1 AMU. Neutrons are similar, also weighing around 1 AMU. They actually weigh around 0.99 AMUs, as you can see on this graph. They look very similar, but neutrons are technically smaller than protons. The difference between their weights is so small that we just round up to 1. Electrons, on the other hand, are very small. And even though AMUs is a very small measurement, electrons still manage to have their weight be almost 0. And the way that we write that in AMUs is that we said their weight is negligible, which means that their weight is so small that it basically means nothing. It adds almost 0 weight, so it just rounds down to 0. So now we're going to move on to the different locations of the atom. So the center of the atom is called the nucleus, and that is where the protons and the neutrons reside. Actually, the protons and neutrons make up 99% of the nucleus's weight. So yeah, the location of the protons and neutrons is both the nucleus, but the electrons actually reside around these rings that we call the electron field. Yeah, and actually, if we were to draw what the electric field or the electron field would look like, it would actually not be much of a line. It actually would just be looking like a ball of gas that electrons are able to move freely. And now that we have the subatomic particles listed, the next step that we can take is actually use these particles to figure out the element of this atom. And how do we do that? Well, first we need to find the number of protons, neutrons, and electrons in the atom. So the number of protons, again, are just the shaded circles. We can count them. So we have 1, 2, 3, 4, 5, 6. We have 7 protons. I'm going to write this down here so we remember. So protons is equal to 7. Let's put neutrons and electrons as well. Great. Okay. So number of neutrons is the not shaded circle. So we have 1, 2, 3, 4, 5, 6, 7 as well. And electrons, which are going to be all of these outer circles. So we have 1, 2, 3, 4, 5, 6, and 7. So actually using the number of protons and neutrons, we could actually identify the element of this atom. And how do we do that? We do that by looking at the periodic table. So looking at the periodic table, we do have a lot of information. For example, if we were to look at boron, we have this number 5 at the top, we have the symbol B, the name of the element, and then this at the bottom, or this number at the bottom, which we'll go into later. But we're actually, what we can go into is looking at, or describing the number at the top and the letter. So the number at the top actually refers to the number of protons. So each element has its own number of protons, where nitrogen, so if we were to look at an atom with 5 protons, we automatically know that's boron, because there is no other element that has that number 5 at the top. So in this case, we do see that we have 7 protons, so we can already identify that the element that we have is going to be nitrogen because of the number 7 at the top. So you know what, this is going to be nitrogen, and we can actually write it the way that we have it written on the periodic table, where we can have it here. The N represents the atomic symbol, which are just symbols that we have for every single element to help differentiate them from each other. So it's like if we were to, instead of writing these long names like we have californium down here, we can just write CF and we automatically know what the element is. So we could write N for nitrogen, which is the element of this, or to the element of this atom. We can write it and actually, with all this information, we could write it like this, but there also is another format called nuclear notation that helps us organize our information better. So nuclear notation is basically when we have an element, let's say we have nitrogen again, and we have a number that we write on the top left side and at the bottom left side. The top left side will be the number of protons inside of the element, or inside of the atom. In this case, we're doing the number of protons is 7, so the number that we write up here is 7. And the number that we write at the bottom is the atomic mass, which is the complete mass of the element, or of the atom. And looking here, we know that to find the mass, we know that protons are 1 AMU, neutrons are 1 AMU, and electrons have a negligible mass, which means that when we're finding the mass of the entire atom, we don't need to count the electrons. We just need to focus on the protons and the neutrons. So to find the atomic mass, what we need to do is add the number of protons plus the number of neutrons. We're going to use P plus to indicate protons, N to indicate electrons, to indicate neutrons, and we're going to use, that'll be fine. And so we see here we have 7 protons and 7 neutrons. So the atomic mass is equal to 7 plus 7, which is equal to 14. And that'll be the number that we write down here. And this is how you write in nuclear notation. And although we do have the number in nuclear notation, we can see that the nitrogen that we have up here is a little bit different than the nitrogen that we have down here. So we do see that the number at the bottom is 14.007, and we have the decimals here. And the question here is, why do we have those decimals? And so the reason why we have the decimals at the bottom is because this represents the mass number of the element. So compared to the atomic mass, which helps us find the mass of one atom, the mass number is the average of a bunch of atoms of nitrogen. So what this is telling us is that on average, nitrogen atoms will have 14.007 AMU. And from what we can take of this is that sometimes there will be atoms with a mass of 14 AMU, but on the very rare occasion, there might be some nitrogen atoms with 15 AMU. But looking at how significantly small this number after the decimals place is, we can tell that nitrogens with 15, with a mass of 15 almost never happens.